For my audience, I'm going to present a new way of looking at things. This is a very creative endeavor for me, so a lot of the things that I say might be flat out wrong. But one thing's for sure, I haven't seen this anywhere on the internet. So those people that say I'm unoriginal, well, I'm going to completely falsify that argument. There are three kinds of thermodynamic work done on the environment. You have convection, which is gas, air, it's hotter, rises, and the cold air falls. And you have convection currents. You have conduction. For instance, you have a flame from a candle heating a large bar of metal, say copper. Actually, I got that backwards. The hotter side should be right here. Hot, cold, okay? Hotter side transfers heat all the way to the cold side. So nothing actually moves per se, as in convection, but the atoms do jiggle around faster. Radiative work, stars exhibit radiative work. They radiate outwards, heating up material through the vacuum of outer space. And what this means is that convection requires atoms and molecules. Conduction requires atoms and molecules. Radiative work does not require atoms and molecules. You don't need those to do radiative work on the environment. Gravitation doesn't require atoms or molecules either. As well, it essentially pulls everything. So what we have is a type of radiative work that's done on environments absent atoms and molecules. So what I'm saying is gravitation and radiative work are very, very similar. In other words, if you have an object that's really large, establishment science like to say the mass is really great, okay? That's why the gravity is stronger, okay? Or it could be larger objects exhibit more radiative work. They radiate more, meaning something to do with thermodynamic energy has something to do with gravitation. They're interrelated. The mass argument was used to justify Newton's theories, to do a mathematical formula. But it might be completely wrong. Because what happens is when the object gets smaller, the establishment people say, oh, well, since it's smaller, so it went from here to here, it must be less massive. The mass is less. Greater than over here, greater than over there, you know, on and on and on. But what could be actually happening is the amount of radiative work it does to its environment might be a lot less. Meaning, the mass argument is bogus. Radiative work might equal gravitation on large scales. This is macro. Macro dissipative systems, I should say. So to put this in a graph, what I would do is this. You have your x and y axis, and what happens is the star, when it's really hot and bright and shining, okay, let's say this bottom axis is gravitational pull. Okay, so you get stronger gravitational pull when you go this way. And mass can be on this side of the graph, actual mass. Okay? Now I'm going to have a hard time explaining this, so hang on. If you have an object which you measure as extremely massive because it has a large gravitational pull, the two actually flip-flop. In other words, all right, where would I put the sun on this? Let's say I put the sun, let's see, no, mass is high, gravitational pull is high. So the sun would be right there. Okay? So the gravitational pull of the Earth would be right here. Low gravitational pull, very low mass. But what could be actually happening is you have a sun which is measured to have a lot of mass because it has a lot of gravitational pull, is actually down here somewhere. Wait, that doesn't make any sense. Gravitational pull, it would be down here. It's actually down there, somewhere around where the Earth is. Because its radiative work is a lot more than the Earth. The Earth obviously doesn't shine, and its actual volume is a lot less. Okay? So what's probably happening is that you have objects which are more similar in mass. So what's actually different about them is they radiate on different levels. So which means the mass argument, meaning that, stars don't lose any mass, could have a discovery inside of it which we were completely unaware of because we were applying mass to everything. Yet we were ignoring the fact that stars radiate by very large amounts. And really, to drive this point home, it should be a challenge for people to find something that is composed entirely of plasma, okay? So it would radiate a lot. Now this is a cohesive object. Any star that radiates in its plasmatic orientation that has a mass equal to the Earth, okay? Or to find an object which is composed entirely of solid material, which does not radiate, okay? Does not radiate, which has the mass of the sun. That's my main point, is we're neglecting an aspect of nature which could hold fundamental discoveries inside of it, which we ignore because we only apply mass to everything, and not realizing that there are other aspects to nature which we should pay attention to. If anybody has any questions or comments, please post them below. I guarantee you're not going to see this anywhere on the internet.